Now it's time to start the session. From here, Tomohide Shibata from Yahoo Japan will talk about AutoFM, an automation platform for the training and inference and foundation models.
I'm Tomohide Shibata from Yahoo Japan. I will talk about AutoFM, an automation platform for the training and inference of foundation models. So let me briefly introduce myself. I'm Tomohide Shibata. I joined Yahoo Japan in 2019, and I am a senior researcher at Yahoo Japan Research. My specialty is natural language processing, NLP. I do research on NLP for Japanese using deep learning and the development of service contributions using the latest NLP technology. I like shogi and go, and both of which I am a Dan grade holder. In recent years, the foundation model has attracted much attention. Fundamental models or foundation models are the models that are trained from large data sets like text and images, which can then be used for various tasks such as QA and reputation analysis. The concept is shown on the right, and the foundation model is the term proposed by the Stanford group in this paper. Foundation models include BERT and GPT-3 models of language processing and CLIP, a multimodal model of language and images. The foundation model has been greatly successful in the areas of language and image processing. This presentation will focus on BERT, one of the foundation models. BERT is a model that Google released in 2018. BERT is an acronym for bidirectional encoder representations from transformers. I will not go into the details today, but it is based on transformer which has been used in various fields in recent years. BERT has achieved significant accuracy gains in a variety of language processing tasks compared to models some time ago. One of the characteristics of BERT is that it consists of two steps, pre-training and fine-tuning. This is an overview of BERT. As I mentioned earlier, it consists of two steps, pre-training on the left and fine-tuning on the right. First, the left pre-study uses a large text to learn the general meaning of words. For example, the Japanese Wikipedia consists of 20 million sentences, and such a large text is used. In the pre-training, guessing randomly hidden words from the words around them, a series of fill-in-the-blanks problems are solved. For example, so just like this, the words are hidden randomly. For example, the hidden word competition is inferred from the surrounding words such as automobile, wheel, and four wheels, or wa, as well as similarly the word ni is inferred from competition or against. By solving these fill-in-the-blanks puzzles repeatedly, you will learn what each word means. Fill-in-the-blanks questions can be generated automatically by hiding random words. In other words, there is no need to manually assign correct answers. Thus, any number of large texts can be used. Pre-training requires intensive computation and takes roughly tens of days. However, the training only needs to be done once, and the trained model is shared. Next, fine-tuning is performed on the right. Fine-tuning conducts learning downstream tasks that you actually want to solve. Here, as an example, we will deal with reputation analysis, classifying whether an input statement is positive or negative. In this case, whether this picture is interesting or not, and well, this film is interesting or not, positive, and when this film was not interesting, this would be negative. Fine-tuning requires manually assigning labels to input sentences. This is usually in the thousands or tens of thousands. Fine-tuning starts with the model learned in the pre-training, and learning occurs via tuning so that downstream tasks can be solved. Unlike pre-training, fine-tuning is relatively quick, finishes in a few dozen minutes to a few hours. This is possible because, as I said earlier, it starts with a model that we have trained diligently in advance. That is an overview of BERT, which can be broken down into 2 steps to learn a powerful model. BERT is a very powerful model, but there are 2 problems in this use. The first problem is that it is not easy to make full use of foundation model like BERT. Accurate understanding of the foundation model requires a variety of knowledge, which is very difficult for engineers unfamiliar with NLP and even for NLP engineers. The second problem is that even if the model can be mastered, developing the model independently in each department would result in a waste. Because foundation models such as BERT are generated, unlike the models of a century ago, there is no need to write code independently for each task. To solve these problems, we are developing a platform to automate the training of the foundation model named AutoFM, so I will talk about it today. This is what I will be talking about today. First, I will explain what AutoFM is, its design philosophy, and the specific system. We then discuss use cases within Yahoo Japan, specifically categorization of search queries, and finally about future prospects.
What is AutoFM? AutoFM is a coined term. The name was created by combining AutoML to automate machine learning with the foundation model, FM, which was explained earlier. More specifically, AutoFM is a platform for automating the learning and inference of the underlying models and is built on Yahoo Japan's in-house AI platform. The aim is to make it as easy as possible to train, examine, and deploy the underlying models. The key concept is to allow users to go from fine-tuning to deployment by simply preparing a training and evaluation file as shown here. In this file, each row represents a single training dataset with the input sentence on the left and the correct answer labels for the input sentence on the right. As mentioned earlier, the correct answer labels must be constructed manually. By providing only the training data in this way, the user does not have to write any code, which presents time-consuming and error-prone implementation. Second, there are 2 main ideas in the design of the system. The first is to avoid dependence on individual engineers by avoiding proprietary code. Avoiding dependence on specific individuals is very important to ensure that the code can be maintained for a long time. For this reason, we have taken the form of a slightly modified version based on the official scripts of the TensorFlow OSS. Also, instead of building our own learning and inference system, we made sure that it runs on top of our in-house AI platform. In this way, we can also avoid dependence on specific individuals. Second, we are always conscious of separating generic codes from the project-specific codes. If project-specific codes are hard-coded into the main program, it becomes difficult to use the same system for multiple projects. To avoid this, we designed the system to be generic, and if project-specific process is required, we take it out of the system. From here, I will describe how to run the system on an in-house AI platform. The first method is to train or fine-tune the model. This is done using a training system, internal system called Lake Tahoe. Fine-tuning can be done by simply placing a training file on the server, as described earlier, and submitting a job, as shown here. Hyperparameters, such search, can also be easily performed, writing a configuration file, as shown here. Here you state that the goal is to maximize accuracy on the validation set. And here you state that you want to search for some combination of epoch number and training rate. You can simply prepare such a configuration file and submit the same job as above to perform a hyperparameter search and obtain the results shown on the bottom right. So again, this mechanism is not newly implemented, but simply uses a mechanism on the AI platform that already exists. The next step is to manage the experiment using MLflow, which is OSS. When fine-tuning is carried out under various conditions, it becomes unclear under which conditions the model of fine-tuning was carried out. So MLflow can be used to manage experiments like the one shown in the picture. One row corresponds to one fine-tuning, and the hyperparameters and accuracy are recorded. In addition, the system's outputs and correct answers are easy to see, which is very important when examining the model. The viewer for the analysis results, as shown here, can be provided to the output of the system, and the correct answers can be viewed easily. Finally, deployment of the model. This is done using a managed inference service called Sark, which is developed in-house. Models can be easily deployed by simply tapping a command, and once deployed, the results of the system analysis can be obtained by simply issuing a command like this. In this example, we are performing the polarity classification task described earlier, and if we enter the input sentence, "I'm glad I bought this book," the system output is positive, and the confidence level is displayed on top of that. So this is a bit detailed, but when dealing with Japanese strings, pre-processing, the process of converting from strings to word IDs, is sometimes necessary. So by hiding that, the user can input Japanese sentences like this.
So this is how in-house AI platform is used. So up to this point, I have explained the basic philosophy of AutoFM and how it operates. So next, I will explain the use cases in Yahoo Japan. As I mentioned earlier, AutoFM is designed to be generic and can be applied to a wide variety of tasks simply by changing the training data. On the left is the polarity classification described in the first example. Like query categorization that we will discuss later, this works just by giving the search query and its category. For example, there is a maritozzo, and this is a recipe for coconuts and so on. And SoftBank is under the category of organization, smart device. Those are also the data. AutoFM does not know that it is clarifying search queries, it is simply given this training data. Although only this example is shown here, there are many internal tasks that can be considered. Considered text classification by BERT and are beginning to be used in various services. So the rest of this section will use the categorization of search queries as an example. Search query logs are essential to understand users' needs and challenges. In analyzing secure search query logs, queries are usually categorized and analyzed by categories such as person or product name. In the query categorization, the problem here is that query logs are very long tail. Therefore, even low-frequency queries must be classified with high accuracy. And in addition, the query logs are constantly updated with new terms and jargon created every day. It is required to correctly classify such new terms. Therefore, we use AutoFM to categorize queries in BERT. BERT was found to achieve very good accuracy in categorizing queries compared to previous machine learning. This is the search queries categorization. We are replacing the general BERT descriptions shown at the beginning with a description of search query categorization. First, the pre-training uses Yahoo's Japan search query logs, not Wikipedia. We use 50 million queries, excluding duplicates. This is because Wikipedia does not cover new words in a timely manner. As it says, this includes YouTube, Yahoo Japan login, and those kind of queries are used. When as explained about generic issues as BERT, they learn some generic meaning of those words. It takes dozens of days to learn a model, and the learned models are shared internally so that they are not learned separated for each project. Next, we perform the right fine-tuning. We have training data consisting of pairs of search queries and their corresponding categories. This is roughly 30,000 cases. Here we have a multi-label classification, which is a problem in setup where a single search query can be classified into multiple categories. For example, SoftBank is classified into two categories: smart devices and companies and organizations. This fine-tuning usually takes only about 10 minutes. Now, I gave the example of Maritozzo earlier. How can Maritozzo be classified as a gourmet? Maritozzo is a sweet that came out a few years ago, as shown here. In the search log used for prior pre-training, Maritozzo is searched with other words such as what is Maritozzo, as well as Maritozzo convenience store. Even those who do not know Maritozzo search the word with convenience store, recipe, and Godiva, we can infer that Maritozzo is a sweet. This same thing is done by BERT. So think of dorayaki as something similar to Maritozzo. Dorayaki is also searched with the words like recipe and convenience stores. For these search logs, solve the fill-in-the-blank questions described earlier. If you compare the two here, guessing the convenience store from Maritozzo and guessing the convenience store from dorayaki and doing the same thing. So from recipe, they are also guessing these two. And if you compare these two, guessing Maritozzo from recipe and guessing dorayaki from recipes are again doing the same thing. As they continue to learn this way, they eventually learn that maritozzo and dorayaki are the same thing, or to be more precise, the same vector representation. Then, right one, fine-tuning is performed. With the training data for fine-tuning, teaching the model that dorayaki is a gourmet food or recipe or cooking. Then, in the left training, having learned in pre-training that maritozzo and dorayaki are similar, it can correctly classify maritozzo as a gourmet or recipe cooking. In summary, new words like maritozzo can be learned from web search logs without manually creating the correct answer. Then, fine-tuning on the right, you only need to manually teach the categories for the core words only, in this case, dorayaki. So, in this way, new words are addressed by BERT's two-step learning framework. This system was evaluated. The number of categories is roughly 50. The name of person, organization, gourmet are included. When evaluated using micro F1, a measure of how well the system's output matches the correct answer, as it says, it was 75.5. This graph or figure shows the accuracy for different text used for pre-training. First, the accuracy is higher using search queries than using Wikipedia. That is orange. And vertically, micro F1. The orange one, that is Wikipedia, is straight line. However, search logs, if the greater the number of search queries, the higher the accuracy. So, clearly showing that the bigger the data, the better. So, you see that the accuracy of Wikipedia's line is more accurate, and the more the number of search queries, the higher the accuracy, and clearly showing the biggest the data, the better.
Examples of system outputs. This table shows queries and the corresponding system output. It's a multi-label classification, so there are multiple categories, and the figure in brackets represents the confidence level, 0 to 1. And closer to 1, the higher the confidence level. As can be seen, even new words are correctly classified, indicating that BERT is very powerful. For example, on the top, auto taxi is classified correctly as title of a film without being affected by the string taxi. Also, bottom 3 is One Piece, which is a typical example of a highly ambiguous query, but it could be classified correctly. So, if you summarize One Piece story, it is classified as manga or animation. And if one enters in the query One Piece ladies, it is classified under fashion. And if it's One Piece 1015, and 1015 denotes the 1015th episode. And this is also correctly classified as manga and anime. So we can see that BERT is extremely powerful. So in this way, queries can be analyzed on a large scale, and the results of the analysis can be registered in a database so that anyone can use them easily. Earlier, we mentioned that the search query logs can be updated to accommodate new terms. Here, we show that the results of pre-trained models in 2021 and pre-trained models trained in 2022. For example, in the 2021 trained model, the term Omicron strain was incorrectly classified under finance and investment because strain is kabu, which is the same as stocks in Japanese. But in the 2022 model, it is correctly classified under health and medical. And also, stealth Omicron is also classified correctly under health and medicine. And also at the bottom, Mog Rider, the stand-up comedian, is correctly classified under celebrity. So in this way, new terminology can be accommodated without having to manually update the data for fine-tuning. And going forward, maybe the model we can build a workflow to update the model on a monthly basis. Future directions. Currently, we handle mainly categorization by BERT, but going forward, we plan to be able to handle token-level classification, mainly named entity analysis, as well as tasks other than BERT, such as generative models like the encoder-decoder model, and tasks for learning sentence vectors in the same way, just by providing training data. We also want to be able to use the widely used Hugging Face transformers as a backbone, although they are currently based on the official TensorFlow 2.x scripts. We also want to provide a web-based interface for training models so that non-engineers can also use AutoFM. By doing this, I hope that AutoFM will be used in more scenes. So here is today's summary. We introduced AutoFM, which is under development. AutoFM is a platform for automating the training and inference of underlying models and runs on our in-house AI platform. We will continue to expand its functionality as we listen to requests from each project. So that was all from me. Thank you very much.
Thank you very much, Mr. Shibata. So from now, under the title Plus Talk, we would like to go in depth of the contents of the session. We also would like to take your questions as much as possible so that we can proceed. So if you have any questions, please press question mark to post your questions. And the questionnaire is Mr. Haru Makita from LINE, so please introduce yourself. Yes, I'm Makita from LINE. Thank you very much for your introduction. I usually use a large-scale language called Hyperclover. Nice to meet you, and thank you. Thank you very much. So, Mr. Makita, listening to what you have heard, what is your first question? Yeah, it was very interesting. Thank you very much for your valuable presentation. So let me ask you some questions. So first, this AutoFM. By handling AutoFM, the server-side engineers do not have to do fine-tuning individually, or rather easier for them to do fine-tuning individually. But looking at before and after that development, what was the response? Yeah, thank you very much. As for before, so the department that can develop the models are actually running and implementing the models. But those who cannot, when they start from the implementation of the models, they cannot actually run those models, or they cannot enjoy the full functionality. And in the case of the system implementations or the users, I think they can use some amount of accuracy.
Thank you. And in your presentation, you mentioned separating the project-specific codes. In case of NLP, the pre-processing can be commonized to some extent. But do you see those type of needs coming? Thank you for the question. For the pre-processing, we use a common tokenizer. And that part will not be project-specific. Maybe I could not explain clearly, but project-specific code means the API output. Depending on the projects, the API output might be a little bit different. This not directly changing the API output, but from that, as I showed in the presentation, the generic part and the project-specific part we have separated.
Currently, there are services for the production environment and for development environment. I think like this, you are building around several environments. Is my understanding right? Yes, there are many ways to use. Largely, so it's for offline batch processing. As I showed you in the second half, so the result of the categorization would be conducted by batch processing, and the result of analysis is used. And also in the middle, I talked about NLP processing. So real-time processing using that is also another one. So in general, there are two types, but the foundation is always the same.
Thank you. About the pre-training models, I think there are a number of pre-training models. And how often are they updated? And can they support or respond to signals? So can you tell me about the frequency of update? Basically, as the generic Wikipedia is fine. But search logs, the distribution is different from generic Wikipedia. In that case, a specific domain text is better. And otherwise, the Yahoo Japan employees, I think there are many services like news. And to what extent you build models for that? And if it's search, maybe we cannot support the signals unless they are updated every month. So we will validate how often we need to develop, to update in each service. So what will be the minimum frequency period? I think search query log will be the most frequent, maybe once in every month.
Thank you very much. So, question from the audience. At Inference, the tokenization, that type of pre-training is closed or sealed. How do you actually realize that? Thank you very much for the question. It's a kind of detailed story, but as I mentioned in the middle, so the TensorFlow code, when this code is used, the part of to be tokenized can be also embed into TensorFlow, which is very convenient. So I use this one.
Thank you. I have a question. The machine learning life cycle, the test data and training data needs to be maintained. So what are your plans going forward? And how do you think about annotation tools? That is extremely important. I talked mainly about models today. But the model part is not really problematic. The problem is how to build the training data. The training data, the most simplest way is to create the training data manually. But other than that, we can use Yahoo Japan Cloud Sourcing or automatically generate from click logs. So I think there are many ways to come up with the data. To achieve high accuracy, we need to have correct annotation from beginning to end. annotation tools can support that and integrate with the system output, we will need that sort of tools going forward.
Thank you very much. Based on what you have mentioned, so it's basically NLP model, but in the future you can also apply computer vision as well as voice. Is that going to be included as well? Yeah, multimodal is also very advanced these days. Language, images, videos. I think there are a lot of scope. So for those requests, we would like to expand to those areas as well.
Thank you. We have a question. All using the project A be using AutoFM, and the platform model created by A can be use that for fine-tuning. So I would like to answer that question. The generated model, sharing that internally, we are coming up with a framework for sharing the models which were generated within the company. We have model hub where everyone can share the model, and we are now trying to do that within our company. So the answer to the question is basically yes. But we want to make it easier to share.
Thank you very much. The next question. So you use in-house AI platform. And in this AutoFM, which part has been implemented with this? And what are the things that you had difficulties? Well, basically, as I mentioned earlier, so OSS, TensorFlow OSS is the base foundation. However, Japanese support and the result of the analysis should be easily visible. So for those core aspects as well as surroundings, so those are basically implemented so that they can be commonly used. The difficulties we faced, well, I didn't feel anything very specific particular, but so if you by setting or hiding tokenization, that's one of the difficulties.
I see. Thank you.